Eso es así. Hombre, se montan hogueras y todo.
NanoSpin-off talk. Today we are very happy to host Alex Julia, who has, of course, a spin-off based in nanoscience. So let me give you a brief introduction about his career journey. Alex Julia, born in 1993, and studied nanoscience and nanotechnology at the Autonomous University of Barcelona. After that, he deepened his expertise by earning a master's degree in advanced nanoscience and nanotechnology. After completing his master in 2016, he joined the Nanostructure Functional Material Group at the Catalan Institute of Nanoscience and Nanotechnology, where he began his PhD in material science. His research focused on developing next-generation chromogenic and emissive materials using micro and nano capsules. Following his PhD, he pursued in technology transfer, equipping him with the skills to bridge the gap between scientific research and business. So they funded a company called Distinkt. This company brings smart inks to the market to combat counterfeiting. So with that, I'll hand the floor over to Alex. So let's start. Thank you.
Thank you so much. Okay, thank you for the nice introduction and the invitation to be here. So today I'm going to explain Distinkt, which is a spin-off company that comes from the ICN2, the Catalan Institute of Nanoscience and Nanotechnology, and also from the UAB, Universidad Autónoma de Barcelona, and CSIC. But I divided this presentation into two different parts. The first part, I'm going to explain a little bit about the research group where I did my PhD. And also the second part will be focused on Distinkt and where we are and where we are in terms of the products that we are going to bring to the market in the near future. So this is the research group where I did my PhD. The name of the research group is NanoSFAN, Nanostructured Functional Materials, and is divided in two different parts. One part of the group is related to health. So we are using nanomaterials for treating brain diseases, tissue regeneration, or infections. And then we have another part of the group that is using chromogenic materials, which are materials that change color or fluorescent properties with external stimulus. And we use them for energy management or energy saving in buildings. So how we work? Well, we start with molecules. These molecules, we play with supramolecular interactions to generate new effects. We structure them in the form of particles or capsules. And then these capsules and particles can be embedded into polymeric films to be applied in different applications. They can be biomedical or energy management and anti-counterfeiting. That is the case of Distinkt. So let's focus on the health part. They play with biomimetics, so inspired by nature, they can obtain materials for different applications. In this case, this is the best friend of one part of the group, that is the muscle. The muscle, they have these proteins that they allow them to stick very hard into the rocks, even underwater. And this is thanks to these proteins that they present these catechol moieties. With these catechol moieties, well, some of the molecules, for example, dopamine, they present this moiety. And with dopamine, they can obtain nanoparticles, they can prepare universal coatings, and also they can prepare freestanding membranes. These membranes can be used, for example, for tissue regeneration. And in 2025, this year, another spin-off born from the same group, that the name is TIRECAT, that is tissue regeneration based on catechol. And as you see here, these are the membranes, very thin membranes. This is how they look like. And here the cells can grow. So that's why they use this for tissue regeneration. But also they have other properties like antimicrobial and to treat infections. And these membranes can also be produced in the form of nanoparticles for therapy and also in some cases for the diagnosis. Then we have the other part of the group that is working with energy management, with chromogenic materials, and we always do the same. We play with phase change materials, with oils, and with molecular dyes. So the interesting point of these phase change materials is that they undergo a phase transition from solid to liquid. In these materials, we can dissolve molecular dyes that can be photochromic, thermochromic, or fluorescent, and they change the optical properties depending on the phase of this phase change material. And what we do is to encapsulate these mixtures, and then we have capsules or structure them in the form of particles to obtain water dispersion of particles to be used as an ink or a coating. And also we can embed this into polymeric films, like you see here, the capsule embedded into a film in this SEM image. So this can be used in different applications as well. There's another spin-off company called Futurechromes that they use this technology of encapsulation oils with photochromic dyes to generate materials that change from transparent to colorful, and then they go back very fast to the initial state. So this is almost in the market right now. Then we can produce sensors that can be activated at different temperatures. And as you see, these are fluorescent sensors. And then we can play with anti-counterfeiting. That is the case of this thing that I will explain in the next slides. So first of all, I would like to start with a little bit of background of my PhD thesis. I work with temperature switchable photochromism. So here you see, these are microcapsules. We encapsulate phase change materials with a photochromic molecule. This photochromic molecule, when it's exposed to UV light, it undergoes a conformational change. And you see here that it's more conjugated, so that's why we observe color. This molecule is in the phase change material in the solid state. But what was interesting in this case is that if we increase the temperature and we melt this phase change material, if it's an acid, it can also interact with the photochromic molecule, opening the form and generating the color. And at this point, we can irradiate with visible light to delete the color. So it's going back to the initial state. And we can move from positive or normal photochromism to reverse photochromism using temperature. So here you see these are microcapsules in the SEM. They present this core shell structure where inside is the PCM with the photochromic molecules. And here you see the powder, how it looks like. And well, in presence of UV, you see the color change, also with temperature. And then at high temperatures, we can irradiate with visible light to color the system. So following the same idea, we work with capsules encapsulating oils with strong or weak acidity. With a strong acidity, these oils can protonate these photochromic molecules, and the protonated form gives a yellow color, and the non-protonated form gives a violet color. So in this case, we were able to produce these powders with different colors just by changing the phase change material that is inside. And in all the cases, by using visible light, we can decolor the system, and it goes back to the initial state. And this can be dispersed into polymer water solution, prepare films, and you see the films that we can put a mask, irradiate with visible light, and you see here how we obtain these patterns that is reversible, because after removing, the system will go back to the colorful state. Then we have, we moved from photochromes to fluorescent molecules. I also developed these systems that are polymeric nanoparticles, where the fluorescent molecules are inside, and then these molecules are aggregated. So if the fluorescent molecules are aggregated, they suffer from quenching of the fluorescence, so you cannot see any fluorescence there. But if we increase the temperature and we reach the glass transition temperature of the polymer, that is a kind of a melting, then the fluorescent molecules can disperse and then give rise to a highly fluorescent state. And this is irreversible because the molecules get kinetically trapped, and that's why you see this change when increasing the temperature. And the good point is that by changing the polymer that we use, we can tune the temperature at which the change is produced. So we can have these high temperature fluorescent sensors. And finally, the last part of my PhD was about these mixtures of, again, phase change materials with ketocyanin dyes and a color developer. So in the solid state of the phase change material, the ketocyanin dye is interacting with the color developer. So it's, the color developer is protonating this molecule here, and you see all the conjugation. That means that the absorption is almost in the near region. So we can have colorless initial state. And then by increasing the temperature, the color developer stopped the interaction with the dye. So there's here we broke the conjugation, and then this moves to the absorption in the visible region. And that's how we change from colorless to color thermochromic materials. And also we encapsulate them and we prepare these films, as you can see here. So we were lucky when I finished my PhD, because this was in 2019, La Fábrica Nacional de Moneda y Timbre came to our facilities in the ICN2. And well, maybe when you hear La Fábrica Nacional de Moneda y Timbre, you think about La Casa de Papel. But they are the money makers of Spain, and also they are producing the passports, IDs, and also tax stamps. And they were looking for possible applications and possible technologies to apply in security field. So they were looking for near light activated materials, and also dynamic materials that can change from one color to another, or from one fluorescent state to another. At that point, Jaume Otaegui was doing the PhD in NanoSpin group, and he was continuing my PhD thesis with fluorescent materials instead of photochromic ones. And he was able to develop a system that responds to NIR radiation, changing fluorescence from one state to another. So we thought that this could be a possible technology that could be interesting for this field in security. But then COVID arrived, and we started contacting with different companies in the security field. Previous to that, I did several courses in business schools like IESE and ESADE, and I was working with MBA students trying to think more in a product and not a technology. And also they help us to prepare a pitch for investors and trying to move from lab to the market. So in 2020, we started contacting. Everyone was responding during COVID, so we could have a lot of meetings with big companies. We showed our technology. They were impressed and they were interested in the materials. So that's why we decided in 2022 to spin out the company, because of the interest of all these security in companies. And yeah, the name of Distinkt is coming from an ink that is different from the rest that are using in the security industry. So the problem that we are facing is counterfeiting. That is a real problem. It's 1.7 trillion problem, and it's affecting a lot of industries. You have to think that 1 out of every 20 products that we have is fake. And this can be the lotion that you put in your skin, or a chip that is present in the car that you are driving every morning, or even a fake pill or medicine that you take. So it's a huge problem, and it's affecting a lot of industries like apparel, jewelry, pharma, electronic components, and the most common ones that are passports and banknotes. So this is affecting economy. It has an economic impact for sure for brands and governments, health problem in case of taking fake pills, also legal consequences in case of using fake passports for organized crime, also in e-commerce for the supply chain, and finally sustainability, because the practices of preparing fake products are not the best ones, so it's also affecting sustainability. So let me explain a little bit about how to solve this problem and how the industry is working to solve counterfeiting. There are different levels of security features. The level 1 are features that you can feel with the 5 senses. So that means that you can see with your eye by tilting a banknote, that you can smell, that you can touch it, and you can see with bare eye. And here, the research is focused on color shifting inks that change the color depending on the angle of vision. Then we have level 2 security features, which they use simple equipment to observe these features, like a UV lamp or an IR laser pen. So probably you've been in an airport or a bank and you see how they check the banknotes or the passports, and they put in presence of a UV lamp and they show these inks that are fluorescent. Then we have level 3 and level 4, which are more sophisticated things like chemical markers or DNA taggants that they can be detected with a PCR or maybe using Raman spectroscopy. So these ones are very difficult to copy, but also very difficult to test. And in this case, the problem is that are very easy to copy. So they have been in the industry for a long time, and people know how to copy. On the other hand, they are easy to detect. That is what the industry wants. So we like to position Distinkt technology here between level 2 and level 3, because we have something that is easy to detect with easy to handle devices like a UV and an IR lamp, but it's very difficult to copy because of the combination of the materials that we use. So let me explain a little bit more the industry level 1 security features and how the nanotechnology is involved in this field. Here you see, to obtain these color shifting inks, they play with nanos and microstructures. So for example, using microspheres or nanopillars or inverse opals, the incident light is reflected in different wavelengths. And depending on the angle, it will reflect in one wavelength or another. And you see here this film, how it changes from green to blue, depending on the angle of vision. And these materials are, well, there's a lot of research on this, and all the security industry is focused on trying to obtain level 1 security features that are very, very difficult to copy. But always is by playing with nanostructures and lithography techniques. And here you see these dynamic threads that are in most of the banknotes that are in the market right now. Then we have level 2 security features, which are the most common ones are the UV fluorescent inks. These inks can be obtained in different ways. So the first one is by using rare earth luminescent materials. These materials, they present specific emission peaks, and very bright. But this is the main problem of these materials, that they have very specific peaks. So if you do an emission spectra, you can know which material they are using and copy it. Then there are a lot of research in new materials like quantum dots and carbon dots, but in some cases the synthesis is very cost effective, so they are not in the market right now. And then organic dyes, which are very bright, also they present high quantum yields, but the problem is that they degrade easily. So in few years, they are not going to show anymore the luminescence. And here you see this is a real banknote of €5 and €50. You see these luminescent inks there. Also, this is a real passport. You see all the luminescent inks present there. And finally, also in packaging of pharmaceutical components, that also these inks are present there. Then we have other type 2 security features. These are IR irreversible inks. And again, using nanotechnology, they use metallic nanoparticles like titanium oxide or vanadium oxide nanoparticles that you cannot see with your eye, but by using an IR camera, you can detect them. So this is also again used in products that are in the market. And finally, the upconverter inks, which are lanthanide doped upconverting nanoparticles based on these lanthanide compounds that they have the property to absorb 2 photons and then emit at a shorter wavelength, so at higher energy. So in this case, it's very interesting because we can use the NIR to activate these systems, and you will observe emission in the visible region. And here you see a banknote and NIR laser pen, and you see how in the dot that you are shining is highly emissive in the green. So, and this is used again in banknotes. And finally, we have the level 3, level 4 security features. I'm not an expert on this, but they are using these DNA tagging technologies. So they design a DNA tag. They can synthesize the DNA. Then we have to encapsulate them because, well, to protect the DNA from the external environment, you can use silica or titosan coating. Then you put this into the objects, and then you extract the DNA. You need to do a PCR, and then you decode the data. So this technique is very difficult to copy, but the main problem is all the process that you need to detect it. So you need very sophisticated equipment and lab testing. So here you see the problem of level 1, level 2 security features is that are static, are very easy to copy. In fact, some of them you can find in AliExpress, so you can buy UV luminescent inks, and also they become obsolete. So that's why here we enter with this new generation of dynamic and fluorescent high security level inks based on nanotechnology. So we play with a mixture of different components. We structure these components in the form of particles, and we can print these particles with an ink in the form of a QR code, in the form of a logo. And in presence of UV light, you will observe how the ink glows. And here you see this red emissive state. And then after irradiating with NIR, this red emission turns to yellowish. And then after removing the NIR source, the system goes back to the initial state, and we can tune the time to recover this state. The good point of this is that we have an encrypted state that we can only see when we expose to NIR. So if you see, like, if you put the UV, you will observe fluorescence. So this is like UV common luminescent inks, and you don't know that you have, again, this state that is encrypted there. So the mixture of these components is protected by a patent that is an international patent, and now it's protected in China, in Japan, in India, Europe, and also the States. So why we are better? Well, basically we have a dynamic effect that change from one state to another, in this case fluorescence, something irreplicable because we can play with the components that we use in these mixtures to generate unique effects. And then we are industrially viable because, well, we are producing these particles or capsules with processes that are used, for example, in the cosmetic industry. So we can prepare these materials in tons. So let me go to the basics of Distinkt. We like to say that we are engineers in the molecular level by playing with a molecular assembling of these different components. So we have the phase change material, we have the dye molecules that are fluorescent, and we have another component that is a photothermal agent that absorbs the light and then generates heat. So when the light comes, this material absorbs the light, generates the heat, produces the change of the phase change material, and then the dye molecules goes from interactive state to be dissolved in the matrix. So then that's how we obtain these color and emission changes. Then these mixtures we structure in the form of particles or capsules. It's important sometimes to encapsulate these mixtures because when we try to put the particles into ink formulations, there are a lot of chemicals present there that can affect the optical properties. So we need to encapsulate to protect from the outer space. And this can be in suspension as water-based things. We can freeze dry to obtain a fine powder, like you see here. And then this powder can also be integrated into films, obtaining the same behavior as the initial mixtures. So here you see that the mixture of the components, we can tune a lot of different parameters. The first one is the color. To tune the color, we need to change the dye molecules, and the effect is different depending on the interaction of these dye molecules. So in this specific case, these molecules, when they are in the solid state of the PCM, they try to interact using an excimer that is emitting in red. And then when we irradiate with NIR, we generate this change of the phase change, and you see how it goes from red to yellow in the places where we irradiate. Then this is another mechanism. This is a coumarin derivative, and in this case, after encapsulating this, is aggregated, so it has kind of quenching, and then the initial emission is low, but then when we irradiate with the NIR, you see how it changes from green to cyan. And finally, we have these molecular rotors, these specific molecules. When they are in solution, they can move freely. So there's no fluorescence because the decay is through this rotation. But when it's in the solid state of the PCM, these molecules are aggregated, so they cannot rotate. And that's why they show this emission. And this is called aggregation-induced emission. And we are moving from an emissive system in the blue, and when we irradiate with the NIR, it goes to non-emissive state. Here you see a video of the inks printed and see how when we irradiate with the NIR, the system goes from one state of fluorescence to another. And after removing the NIR, the system goes back slowly to the initial state. So here is just by changing the dye, you see that we can obtain different effects. This red to yellow, this green to cyan, and this rainbow effect that goes from orange, red to yellow. Then, as mentioned, this is going back to the initial state, and we can tune as well the time to recover this state. How? By using different phase change materials. So imagine that we are using a phase change material that the melting point is very close to room temperature, then the system will take longer to go back to the initial state because it has to solidify again, so this process is slowly. But if we use a phase change material that is, it has a melting point very high above room temperature, then the system will go back very fast. So we can tune this time, and also we can make irreversible systems. Depending, we can write a message and we'll be there forever. So here you see the spectra of these two powders. In this case, when we irradiate with NIR, it goes from this red emissive state to the yellow. And after removing the NIR, it goes back to the initial state in 10, 20 seconds. This is this case. But in the second case, as you see in the video, this is activated and it maintains the fluorescence. So here you see after activating with the NIR, the system remains active with this yellow emission. This is interesting because then we can do several things with the time response. One thing that we can do is unique security patterns. So this is what we observe when we irradiate our materials with a NIR. You see this dot changing from red to yellow. But what happens if we use 3 different particles that or capsules that they go back at different times? So in this case, this goes back in 10 seconds, this in 5 seconds, and this one in 2 seconds. So we can combine these two or these two to obtain new effects. Like for example, these 2 concentric circles of fluorescence. So by combining type 1 and type 2, we have this specific pattern, type 1 and type 3, this one, and finally type 2 and type 3, this one. And we can also combine the 3 of them to generate these 3 concentric circles of fluorescence. This is to obtain unique security patterns that are almost impossible to copy. Another thing that we can tune is the power. So we can play also with the NIR power to activate the inks. At certain power, the ink is not going to be activated, but if we increase this power, we have certain threshold where the ink is activated. Then the wavelength in the near region. So we can use photothermal agents that absorb in a specific wavelength. In this case, 780 is the maximum. In this specific case, it's around 830. And we can also have other materials that absorb in the whole region, so we can activate with visible light as well. And here you see that we can tune, we can activate our materials with 780 nanometers or 850. And we can decide depending on the material that we use. And finally, the size of these particles or capsules. The synthesis method by using, using an emulsification process. So depending on the force of this homogenization, we are going to reduce the size of our materials. And we can go from 8 to 10 microns, reduce it to 200 nanometers. And this is very interesting because in some cases, some printing techniques in the industry, they need to use very small particles, for example, inkjet printer. So that's a good point, and that's how we ended up printing with inkjet. Here you see, once we have all the materials, we need to print this, and we test it with screen printing. It's this technique that you use a mesh with a pattern and squeeze it, and you put the ink there, and then you press it, and the ink passes through the mesh, and you can print logos or, in this case, a QR code. And after irradiating as well, the system maintains the properties. And then with inkjet printers, we also could print in glass. You see these QR codes that also change from red to yellow, and with good resolution. And this is because we managed to reduce the size of our particles and capsules with down to 200 nanometers. So with the QR codes, it's something that very interesting because we can encrypt information with these QR codes. Here you see this QR code that changes fluorescence from red to yellow, and only when it's in the yellow state, the mobile phone can detect the QR code. So it's the way to authenticate products. Moreover, we can do other things like mixing, as I mentioned before, different particles that turn back at different times to generate QR codes that, when activated, goes to this green state, and then over time is going to different fluorescent states, going to yellow, then orange, and then red. So maybe we can have a software able to detect only the orange state, and the information is encrypted over time. This is the way to secure products. And then finally, we can print different pixels with different inks, and you see how this ink is activated first, these two pixels, then the other, and how it goes to the initial state that seems that the ink is alive. So moreover, how to detect these fluorescent changes. So we started a collaboration with another spin-off company that is, the name is Color Sensing, and they are developing a mobile app that is able to track true colors. And we wanted to see if we can detect also fluorescent changes. So these are the QR codes that they are using. And we print our inks in 1 pixel of the QR code. In presence of UV light, you see the red emission, with NIR, the yellowish, and then goes back to this state when removing the NIR. So they were able to detect the color transition from red to yellow. And also the interesting point is that they were able to detect with the mobile phone how it goes back to the initial state and the time that lasts to go to the initial state. So this is kind of a fingerprint of every ink that we can produce, and we can detect it with a software. So this is a good timing for us because, well, in the news, everyone is taking care about counterfeiting. Ferrari wants to reward you for reporting fake stuff. Also, Gucci and Louis Vuitton taking care of counterfeit products. And also, for sure, pharmaceuticals or counterfeit alcohol is a problem because it can affect your health. So also, we are in a good moment because there is a new opportunity. The European Commission in 2027, they want that every product in the market has their own digital product passport. And what is this? The digital product passport is a certificate, a digital certificate, where you can find the product information, the product history, certifications, the carbon footprint, and also the recycle instructions. And yeah, every product in Europe should has this certificate, but how to connect this digital certificate to the real product? So the way to do it nowadays is through traditional QR codes. The problem of these systems is that are hackable. They are lacking security layers, and well, they can easily manipulate, changing some squares to generate another information or to copy them. And then the other possibility is RFID tags like NFCs. But the problem of these systems is that also are hackable, are fragile, and they can interfere with electromagnetic fields. So that's why we have this new solution with our inks in the form of QR codes. We can put our ink in different parts of the QR codes that goes back at different times and encrypt the information. So we have this encrypted security, thousands of encrypted points here. Then we can print this directly into the product because we can use industrial printing techniques like screen printing or inkjet. We have these patented nanoparticles that they can change in one time or another with one color effect or another. So we have a lot of versatility as well. And we can print it into different materials like glass, polycarbonate, textile. So we have this solution that we say that we have like a kind of lock and key solution. The lock for us is the ink that can change from one state to another. And then we have a reader that can detect these fluorescent changes and then authenticate the products. So our idea is to end up printing our QR codes into physical products, like in different places, like apparel, jewelry, shoes, then use the UV light and NIR to generate the changes, read it, and after this, we can generate a digital product passport, a certificate that is safe in the blockchain. But how to obtain these changes? So as mentioned, we need the UV and also the NIR light. So we are working on a prototype of a reader and activator. In this case, this is the prototype that we are producing. This is a UV source with control electronics that we can use this button to activate the UV. Then we have here the sample with the QR code, and we have a filter. So then with your smartphone and your camera, you can detect the fluorescence and the changes. So then with this device that we have the prototype, but we need to refine it a little bit. And we are also working on a software with people from India that is developing this software that is able to read these fluorescent changes with a machine learning algorithm. So they can learn how the color transition is produced, and also the time that takes to recover the initial state. And this will generate a certificate where you can find the origin and the information of the raw materials, CO2 emission tracking as well. And also this will be checked in every point of the supply chain in order to be sure about the authenticity of the products, and also to obtain information about the tracking during all the supply chain. So this will have this green passport data. Then the only problem that I see here maybe is this reader that we need the UV lamp, and this is only for the supply chain, but the end customer cannot detect these QR codes. So we are working with new inks that can be activated with a flashlight of your mobile phone. So everyone at home can use this flashlight to activate the inks. We are working with new materials. These materials are crystals where are embedded organic molecules, organic dyes that are fluorescent. And it's interesting because these fluorescent dyes, when you activate them with UV or visible, they decay through emission in fluorescence. But when they are trapped in these crystals, they can go this intersystem crossing, the triplet state, and then you generate the phosphorescence. And this afterglow is for a few seconds. So here you see these crystals, and you see how it goes back to the initial state after activating with a visible light. Here you see the ink. Here you see my mobile phone activating with a visible light of the flashlight, and you see how it glows and then slowly goes back to the initial state. And the idea is to generate QR codes or logos that can do this specific effect. So the idea is to end up in different products, wines. This is the product that is most counterfeit, the AirPods, also in oil. And we can print, instead of QR codes, we can also print logos to verify the authenticity. We will contact in the near future these brands. With some of them, we already had conversations. And then we will also partner with printers like HP or Honeywell or Nagels. We will partner also with Cardano Foundation, that is a blockchain company, in order to put all the digital certificates. And yeah, we hope to start a POC, a pilot with some of these companies in the next months, and end up at the beginning of next year with a product in the market. Here you have the team, me and the co-founder. Then we have Luca Benza, which is the CEO. I met him in one of the ESS course that I did, and he's an MBA and is taking care of all the business part. Then we have a group of scientists that are chemists and nanoscientists that are helping with the product development. And then we also were in Berkeley in an accelerator program. We met a lot of people there. We have two advisors from this course, this Bruce Bergford and Mark Miller, which know quite well the product and help in networking and how to address the market. Then we have Ilan Berker, which is worked in Microsoft and is taking care of the software part with the Indian people. And Sadie Rainey, that is a blockchain expert, and that will help us in the future with these digital passports that will be in the blockchain. And finally, Javier Garcia, which is an expert in the printing industry, have been all his life in HP. So yeah, I would like to end saying that you have to think in this thing because your security matters.
Thank you, Alex. I'm very impressed about your company and also the very huge company that have contact with you. It's amazing. So I would like to ask if anyone has a question to Alex. Reyes, you have been writing.
Yeah. No, but first, the students, you have any questions? Not that you want to leave, but.
Yeah.
I'm just curious, how well the quality of the print, I mean, it's gonna be based on the spec, right? I mean, is it going to be like the one that we print in the paper? I mean, it's gonna be easily removed, or how good is the quality? And also, are you already test like for skin? Is it like safe for skin and stuff?
Yeah, in this case, we are trying to produce the pigment, so in powder form. So that's why we encapsulate these particles. So then these pigments can be dispersed into existing ink formulations. So the existing ink formulations are, probably you can print with industrial printing techniques, and if you try to remove it, it's not going to be removed. So yeah, that's the way we want to be integrated into existing systems, because it's the easiest way. We are not producing our inks. And then the second part is also interesting. In this case, the answer is no. But we can work also with some organic materials that can be biocompatible for skin, but it's not our purpose right now. We can know how to do it in the future, but also it's not the purpose of this company. But in the group, they are working on this as well.
Thank you.
You're welcome.
My question.
You mentioned that La Casa de la Moneda first focus on your product,
Yeah.
but then you make some modifications about the type of freckles and the mix and all of that. So when you will sell your product to other companies or the branches that you mentioned at the last part, how you will manage, or I mean, is part of the companies from La Casa de la Moneda, or
No, in
how
fact,
you will relate?
with La Casa de la Moneda, they were interested and they wanted to start a project with us, but at the end we were not starting a project, so we decided to contact security ink producers because we knew that La Casa de Papel was very interested in our products, and that's it. But with La Fábrica de Moneda y Timbre, the problem is that they want their technologies. So they want to start a project with you in order to have the patent as well, and also the rights to commercialize this. And in our case, we decided to go alone, and I think that for us is better.
I have a question. I mean, how do you consider it's the difficult part to scale up? Because, for example, in nanotechnology, you have the problem that you can have a synthesis in the lab and then go to the industry.
Yeah, in this case, in the group that we do quite a lot of applied research, we always think about the possibility of scaling up our materials. So we use a mixture of components that are organic that you can buy in large scale. Maybe the only problem can be the dye, but we can buy it as well, and it's a small amount that you have to use. And then we need an encapsulation process, but this process is done in different industries, like cosmetics. They use, or detergents, they use capsules that are in presence in the textiles. And then when you do like this, they break, and then you have the perfume. So these are techniques that are right now in the industry. So we just need to prepare the mixture of our components to send to these companies that they can produce capsules in large scale.
So thank you very much. As Laura said, I am very impressed. It's a very, very nice technology, and I'm sure you will go up. So we're lucky that you couldn't hear at the very beginning, because then you would not be reachable. Okay, so I have first a question concerning patenting. You show your PhD and your publications that are previous to the company foundation. So you already patented at the very, very beginning, or how it was?
Yeah, in fact, this technology, as I mentioned, a PhD student, Jaume, was working with this specific technology. So when the La Fábrica de Moneda y Timbre came and was looking for NIR systems with dynamic effects, we thought about the possibilities there, and they decided to patent in 2019.
Curiosity, because of the field that I'm working, you said that in this level 3, level 4, there is also the option of Raman spectroscopy.
Yeah.
How is this developed, or do you know in which state is that part?
I know that I don't know much, but it's true that they are also working with SERS, because they want to increase the signals, and but again, it's difficult to detect it. So yeah, in some cases probably banknotes or these high security applications is very good, because it's very difficult to copy. But for our purpose, it's a little bit different, and we are using systems that are easy to detect. But yeah, it's another option, the source, yeah.
I was also even thinking in the crystallography patterns that you have there with this periodicity, you can include in there the.
Yeah, yes, there's
That's not that.
Yeah, there. In fact, that's the idea for the future as well.
Because you already have this part in the in the manual. Okay. And also there are a lot of curiosity. The spin-off company of the color sensing. You mentioned that is from India, or
no. Color sensing is from Catalonia as well. They are in the UB. So yeah, they have this software, and also they are producing inks that change color with temperature, and they are using this for food packaging to see the cold chain of products. But they are mainly the main part of this company is the software that they can detect color changes with this specific color. Yeah.
And about preparing let's say the add-on for the iPhone or for a phone that you are in that part.
Yeah.
What are the main difficulties there to include the UV light here, and because I saw that it's small.
Yeah, we did. Yeah, well, this is small for us. It's huge. We want to try to miniaturize this, and yeah, we were working with an engineer that was working in ICFO, another institute, and well, he started another spin-off with something similar for the mobile phone to check if you have if you are exposed to the UV or not with this sun cream. So he had like this prototype, and we just changed a few things to activate our inks, and that's why we have this prototype right now. But yeah, the idea is that this can work with one or two mobile phone. Because every smartphone is different, the camera is different, so at least one or two, and then to use this, for example, an iPhone during the supply chain with this specific device to generate the changes and read it.
Thank you very much. You're definitely distinct.
Thank you so much.
Mentioned that you were using machine learning to understand how the inks change and everything. Do you think that would pose like a problem in the future? Like you said, it cannot, like it is hard to copy this technology now, but in the future, like, I don't know, like to what extent we can trust AI and machine learning, but do you think it's hackable in the future? Like, would it still be hard to copy?
Yeah, the thing is that we have our ink that is that we can play with the time to recover the initial state, and depending on the materials that we use. So it's like a unique fingerprint for each product if we want. And then we train the ML algorithm to detect these specific changes. So you need both things, the hardware and the software, to make the final system. And the question is very good, and the answer is that probably in the future, maybe in 10 years, people can copy this. So it's try to get ahead several years from counterfeiters.
No more question? I can do a question?
Sure.
Okay, you mentioned there are different type of inks, and also that organic inks are the most easy to degrade, I understood. But I saw that most of the inks were organic inks, no? So that's why the reason to choose this.
Yeah, exactly. Yeah, the main problem of our system is the light fastness. That nowadays the inks last for at least 2-3 years, but we are trying to reach this 10 years window. So we are by playing with the capsules to add other components inside, like stabilizers, antioxidants, UV absorbers. We can improve quite a lot the light fastness of these materials. But it's also thanks to the capsules that we can embed there in contact with the dye molecules, these stabilizers.
Because the degradation is under the normal light, no? Because
Yeah.
Also there are ultraviolet and
Both, yeah.
yeah,
The UV and also the sunlight.
I understand. And the second question is regarding to the size of the particles.
Yeah.
You mentioned that in the inject printing, it was better to have small particles, no?
Yeah.
So it's very difficult to work in terms of security with these small particles. I'm asking that because we had a collaboration with a company, with a paper company, and they didn't want to work with very small particles because in terms of security,
Safety.
safety.
Yeah. Yeah, in this
was much
case,
more complicated.
yeah, in this case, is if we want to print with an industrial inkjet printer, yeah, you just need like a water-based thing and disperse the particles. We are using materials that are non-toxic, so I don't think that will be a problem. But it's true that all the industry, the security industry, is working quite a lot with offset printing, screen printing, and flexo. So we tested inkjet because I think that is the future, but nowadays the industry is prepared only for the others. So in fact, the product that is ready for the market is around 2 to 5 microns. So, but yeah, we tested inkjet because allows us to also put the inks where we want, and yeah, it's more complicated to counterfeit.
Okay.
And thinking in the practical. So at the end, how much is the amount of your particles that you have to put in a normal ink? And of course, how much will be the expected cost of your inks?
Yeah, yeah. Well, the amount is around 20 to 40%. Depends on the ink, and also the brightness that we want to see after printing. So it's true that the red emissive state is not very bright. So if we want to see this red emissive state, we need to concentrate more, like 40%. But the secondary emission, the yellow one, is very bright. So if we don't want this initial emission, we can play with 20%. And the cost, well, in this industry, you can find UV luminescent inks that cost between 500, 1,000 per kilo. We want to be around 2,500 per kilo, something like this. And the margins that we have is huge because we are using carbon-based materials and that are not very expensive. And the procedure to prepare these capsules is not also very expensive. So the margins are huge in terms of selling the pigment. But selling the pigment is just like a business model that you can sell the pigment until a certain point. But then the idea is the final solution that then you will be in every product. So, yeah.